Our task is to find the height at which can drop a toilet paper in free fall so that it hits the ground at the same time as a toilet paper roll that is unraveling from a height of 2 meters. The laws we will be using in this derivation are conservation of energy and kinematics.
So, the first rule, we're gonna call the roll that is in free fall, roll number 1. So, since it is just in free fall, all of its potential energy from gravity is converted into kinetic energy right before it hits the ground. So, PE1 equals KE1. And potential energy is equal to mass times gravity times delta y. So, mg delta y. And the formula for kinetic energy is 1/2 mass times velocity 1 squared, where velocity 1 is the velocity of the paper towel roll right before it hits the ground. And since we have mass on both sides, we can cancel that out. That equals 1/2 velocity 1 squared. And then we can do some simple algebra to get a formula for the velocity right before it hits the ground. So the one that we'll be dropping and rotating and unraveling, we're going to call roll 2. So for this one, its gravitational potential energy equals its kinetic energy from falling down, plus its rotational kinetic energy. And for this one, we know it's going to be dropped from a height of 2 meters, so 2gm equals 1/2 mass times velocity squared plus 1/2 moment of inertia times angular velocity squared. So the formula for a hollow cylinder for its moment of inertia is I equals 1/2 m outer radius squared plus inner radius squared. So we can plug that into here and get 2gm equals 1/2 mv squared plus 1/2 m r squared plus r squared times angular velocity squared. And angular velocity is equal to tangential velocity over radius. And because the roll is still going to be falling, its tangential velocity is equal to the velocity of which it is falling. So that means 2gm equals 1/2 mv2 squared plus 1/4 m r squared plus r squared times v2 squared over capital R squared. So then we can just do a bit of simplification here, and we can take out m from everything. And we can further simplify this a bit, because 8g equals 2v2 squared plus v2 squared plus r squared plus r over times r squared over capital R squared. And all of this becomes, since we know capital R, or the outer radius, is equal to 0.065 meters, and the outer radius, little r, is equal to 0.0225 meters, we can plug that in here to get 8g equals 2v2 squared plus v2 squared times 0.065 squared plus 0.0225 squared over 0.065 squared. And this becomes 8g equals 2v2 squared plus 1.12 v2 squared becomes 8g equals 3.12 v2 squared. And once we do a bit more simplification, we get v2 equals the square root of 8 times 9.8 over 3.12. So we'll be using a kinematic equation to find a ratio between height and velocity. So we know that delta y is equal to final velocity plus initial velocity over 2 times time. So we know that the initial velocity is 0 because we're dropping them from when we're holding them. So that means delta y is equal to final velocity over 2 times time, and we can use some simple algebra to manipulate this to solve for t. So it becomes 2 delta y over velocity equals t. And we know that both times have to equal each other. The time for the one being dropped from free fall and the one that is unraveling. So we have 2 delta y1 over velocity 1 equals 2 delta y2 over final velocity 2. And since we have 2 on both sides, we can get rid of that. So now we have our ratio of delta y over 1, delta y1 over v1 equals delta y2 over v2. Okay, so now we have our ratio. Delta y1 over v1 equals delta y2 over v2. So, as you know, v2 is the one that is being unraveled. And in the previous part, we found that velocity 2 equals the square root 8 times 9.8 over 3.12 meters per second. If we just simplify that, we get 5.013 meters per second. And then we also know the height that is being dropped from is equal to 2 meters. And we do not know delta y1, as that is a variable we're trying to solve for. And then velocity 1 is equal to the square root of 2 times g times delta y. And now we can plug that in here. So we get delta y1 over the square root of 2 times 9.8 times delta y1, which equals 2 over 5.013. And we can simplify that to be square root of y times divided by 2 delta y equals 0.4. Then we can multiply both sides by this value. We get delta y equals 0.4 times the square root of 2 times 9.8 times delta y. And then we can square both sides to get delta y squared equals 0.16 times 2 times 9.8 times delta y. And then we can simplify that to become delta y squared equals 3.136 delta y. And we can divide both sides by delta y to get delta y equals 3.136 meters. And this is the height that you would have to drop, the one in free fall, to take the same amount of time to fall as the one that would be unraveling. So our results show that if you want a paper towel that is in free fall to hit the ground at the same time as a toilet paper that is unraveling at 2 meters, we'll need to drop the first one from a height of 3.136 meters. And this shows that conservation of momentum is true. So assumptions that we had to make for this result to work. We had to assume that there was no friction, which means we also had to assume that there was no work done on the system. And also we had to assume that gravity was equal to 9.8 meters per second squared.